Hello everyone, my name is Junhao Zhong. I am presenting our CVPR paper this year, The Enemy of My Enemy is My Friend, exploring inverse adversaries for improving adversarial chaining. In this paper, we analyze the unnecessary or even harmful alignment between misclassified examples and propose a novel adversarial chaining framework based on the inverse version of adversarial examples. Our method thus promotes the aggregation of adversarial examples to the high likelihood region of their belonging classes, which can enhance the adversarial robustness of the target model. I will first introduce the concept of adversarial examples. Adversarial examples, they are tailored inputs specific to certain neural networks, which can cause a strong disruption during the inference stage. Take the panda picture as an example. We can obtain the corresponding adversarial example by adding a visually undetectable perturbation. The adversarial examples can typically cause a misclassification with high confidence, and technically we can obtain them by image-level gradient ascent. Obviously, adversarial examples can cause a huge security threat to the current society. Therefore, improving the robustness against these malicious examples can be a crucial point for current AI applications. Adversarial chaining can be a standard to defend against adversarial examples, which can enhance the robustness of neural networks. This can be achieved by solving the minimax game. We generate adversarial examples during the inner optimization, and we try to lower the loss of these malicious examples in the outer minimization. The main goal of adversarial chaining is to establish a robust decision boundary that is not only for clean examples but also for adversarial examples. Generally, this KL divergence during adversarial chaining encourages the prediction of clean and adversarial examples to share the same probability distribution. However, this distribution alignment can further undermine the robustness when clean examples are misclassified, resulting in wrong guidance during adversarial chaining. So, the key problem is that does this misclassification affect the robustness? To answer this question, we study the accuracy on two groups of data. We rank test examples based on the cross-entropy loss values in increasing order and divide them into two equal halves. For figure A, even a small perturbation can induce a drastic accuracy decrease, while for figure B, the robust accuracy of bottom 50% suffers from a heavier drop than that of top 50%, especially under larger attack strengths. This indicates that the adversarial counterparts of low confidence or even misclassified examples they are also misclassified, and therefore the distribution alignment between two misclassified examples can have a harmful effect to the establishment of adversarial robustness. The natural intuition is that adversarial examples have higher loss values compared to their natural examples, and contrary to harmful adversaries, we propose inverse adversarial examples that are created by minimizing the loss. For example, iterative gradient descent at the sample level as an inverse procedure of adversary generation. Precisely, inverse adversarial examples can be more possibly to be classified correctly, and our inverse adversarial examples can correct or regularize the misclassified examples. We can thus use them as the reference for distribution alignment. We further design an universal inverse adversary generation strategy for efficiency. Specifically, each class has a universal perturbation to reduce the objective loss. In this way, we can find a shared direction, like universal inverse perturbation, to reach high likelihood regions, which can also mitigate the individual noise between different examples. When we obtained both the adversarial examples and inverse adversarial examples, we can conduct a regularized distribution alignment between them. We also start to enable a momentum mechanism to stabilize the chaining process. We compare our proposed method with SOTA adversarial chaining approaches. Our method can achieve a better robustness without compromising much natural accuracy. Note that we also propose a one-off strategy to enhance the efficiency of our method. We also combine our method with the SOTA single-step adversarial chaining methods. We can easily observe that our method can serve as a plug-and-play component for boosting both natural and robust accuracy. The additional time cost is also acceptable. In addition, we consider the use of additional DDPM synthetic datasets to further enhance adversarial chaining, especially under different network architectures. Our proposed method also achieves SOTA results in terms of natural performance and adversarial robustness. Furthermore, our proposed inverse adversarial chaining method can effectively adapt to higher attack strengths. We also analyze the common phenomenon of robust overfitting in adversarial chaining. Adversarial chaining mainly suffers from robust overfitting issue resulting in robustness drop on test set. We illustrate the learning curves. The standard adversarial chaining heavily suffers from robust overfitting. The arrow keeps going up, while our method does not suffer from the robustness reduction, especially during the adversarial chaining. In addition, we can also observe a trade-off between natural accuracy and robust accuracy when fine-tuning the hyperparameter lambda. The robust accuracy improves when lambda increases, while the natural accuracy decreases. Finally, we discuss the reason why our method is effective. We compare our method with the SOTA method chase. It can be seen that our method can bridge the robust accuracy gap more effectively. We can also enhance the robust accuracy of the bottom 50% group. In addition, we observe that the inverse adversaries of our method are prompt to be classified correctly. And let's see the accuracy gap between our method and the SOTA method in the right figure. And our method outperforms the SOTA method at weak attack strengths like epsilon less than 8. However, the SOTA method obtains better results than our method when facing strong adversarial perturbations. In other words, our method sacrifices the robustness against larger visual perturbations to enhance the robustness against smaller ones. In conclusion, we analyzed the harmful alignment paradigm between misclassified examples during adversarial chaining and proposed a novel adversarial chaining methods based on an inverse version of adversarial examples, and extensive experiments demonstrate the effectiveness and generalizability of our method. And that's all. Thank you so much for your attention.